In this video, we'll introduce the lasso, picking up right where we left off with ridge regression. We'll see how a small change to the ridge penalty gives the lasso a powerful new ability. Then compare the two methods side by side and finish with how cross-validation helps us choose the tuning parameter. As we saw at the end of the previous video, while ridge regression shrinks coefficients towards zero, it never sets any of them to exactly zero. This means all predictors are retained in the final model, even if some have minimal influence. The lasso overcomes this limitation. Here are the least squares estimates for a model with 6 predictors before any penalty is applied. Positive coefficients extend upward and negative ones extend downward. Now we apply the ridge penalty. Keep an eye on the heavily penalized coefficients, beta 2, beta 3, and beta 6, highlighted here in yellow. Every coefficient shrinks towards zero, and these 3 become very small, but they remain non-zero. All 6 predictors are retained in the model, making it harder to interpret which predictors truly matter. The lasso uses a different penalty called the L1 penalty. The lasso coefficients are obtained by minimizing the RSS plus lambda times the sum of the absolute values of the coefficients. The L1 norm of the coefficient vector is simply the sum of the absolute values of its components. This contrasts with the L2 norm used in ridge regression, which instead sums the squared coefficients. Unlike the L2 norm, the L1 norm can force some coefficients to be exactly zero when lambda is sufficiently large. This happens because the absolute value penalty keeps a constant pull on every coefficient no matter how small it gets, while the squared penalty's pull fades away near zero, shrinking coefficients towards zero without ever quite reaching it. Let's see this in action. We start from the ridge regression fit we saw earlier, where all 6 coefficients have been shrunken but remain non-zero. Now we swap the ridge penalty for the lasso penalty. Keep an eye on beta 2, beta 3, and beta 6, highlighted here in yellow. Every coefficient shrinks, but these 3 are driven all the way down to exactly zero, while the other 3 shrink only slightly. Only 3 predictors remain in the model. This automatic feature selection makes the lasso particularly useful for creating simpler, more interpretable models that often generalize better by avoiding overfitting. Now let's compare ridge regression and the lasso side by side, looking at their constraint formulations, their behavior on a simple example, and their geometric interpretations. Recall from the previous video that ridge regression can be written as minimizing the RSS subject to a budget constraint, where the sum of the squared coefficients must be at most s. The lasso has the same alternative formulation, except the constraint uses the sum of the absolute values. In both cases, the budget parameter s controls regularization strength. Smaller s means stronger regularization. Consider a simple special case where we minimize the sum of y minus j minus beta minus j squared. This lets us see the difference between ridge and lasso shrinkage in closed form. For ridge regression, each coefficient is shrunk by the same proportion. Beta hat rj equals yj divided by 1 plus lambda. Larger coefficients are reduced more in absolute terms, but the relative proportion of shrinkage is uniform. For the lasso, the result is soft thresholding. Each coefficient is reduced by a constant amount, lambda over 2. If a coefficient's absolute value is less than or equal to lambda over 2, it is set to exactly 0. This is why the lasso performs feature selection. Now for the geometric interpretation with 2 predictors, extending the picture we built at the end of the ridge regression video. The ridge constraint again forms a circular region in the coefficient space, while the lasso constraint forms a diamond shape. The green point is the unconstrained OLS solution, and the dotted green curves are the RSS contours. Every point on the same contour has the same RSS. The key insight is in the shape of the constraint regions. Watch the RSS contour expand outward from the OLS solution on the ridge side. Because the circle has a smooth boundary, the contour first touches it at a point off the axes, where neither coefficient is exactly 0. But the diamond has sharp corners at the axes, where one coefficient is 0. As the same contour expands on the lasso side, it is much more likely to first touch the diamond at a corner. Here it hits the corner where beta 2 equals exactly 0, so that coefficient is eliminated from the model. This is why the lasso performs feature selection while ridge regression does not. Selecting the right value of lambda is crucial for both ridge regression and the lasso. Cross-validation is a widely used method for choosing this tuning parameter. The process involves 4 steps. First, choose a grid of candidate lambda values. Second, for each lambda, compute the cross-validation error. Third, select the lambda that gives the lowest cross-validation error. And fourth, refit the model on all available data using the chosen lambda. In general, ridge regression tends to perform better when many predictors have coefficients of roughly equal size. The lasso excels when only a small number of predictors have substantial coefficients and the rest are near 0. Since the number of relevant predictors is not known beforehand, cross-validation can be used to determine which approach, ridge regression or the lasso, is better suited for a particular dataset. And that wraps up our 2-part look at shrinkage methods. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.